So our third speaker today is Dr. Holger Busch from Infineon Technologies, where he's the principal engineer in formal verification. His talk today is on efficient methodology for mutation coverage collection of formal property checking. He studied at the electrical engineering at RWTH Aachen, Germany, and also obtained a PhD from Brunel University in the west of London in the UK. He worked at Siemens Central Research and Infineon Technologies and has decades of experience in formal methods, digital design, automotive safety, and his areas of interest include EDA, digital hardware design and verification, formal methodologies, functional safety, and verification automation. He holds several patents and currently his position, as I said, is principal engineer in formal verification at Infineon. He's based in Germany. Over to you. Thank you, Holger.
Yeah, thank you, Mike, very much for the introduction. And hello, everyone. So I'm directly going to the agenda. So we'll start. Maybe I switch on the laser pointer. Yeah. We start with an introduction to mutation coverage and EDA-Tools supporting it. And then in the next two sections, we summarize the two main phases of the formal mutation coverage flow, which are preparation of design and properties and the collection of fault detections in a property checking environment. Then we'll take a look at approaches for performance improvement and go through a few simple user commands for running the automatic procedures. After a summary, any questions are welcome. So let us start with some background about the mutation coverage. The overall goal of all structural coverage-based metrics is to provide criteria for assessing verification quality and completeness for sign-off of a design module and for project management to assess verification progress while verification is still ongoing. In simulation, structural coverage metrics have been used for decades. For formal property checking, corresponding approaches are less established. Nevertheless, meaningful criteria for assessing verification status and finalization are also needed, of course, for formally verified modules. It has been shown that mutation coverage is applicable to simulation-based and formal verification. In contrast to classical code coverage metrics, mutation coverage not only depends on the activation of design code, so that a statement has been reached or a block condition has become true, but also functionality being checked, so really being verified, which means the effect of the execution of a statement or evaluation of an expression is verified. Mutation here means that the design is instrumented with additional distorted logic function, which can be selectively switched on instead of the regular function. For this purpose, multiplexes are inserted into the design, which are controlled by fault-enabling inputs. When simulation-based verification or formal property checking are applied, each fault can be individually enabled by setting a corresponding control input to 1. If a previously passing test case or property fails with a specific enabled fault, this fault is classified as detected. So in this case, the failure of a proof or test case is desired because this is an indication that this fault is detected, really. For formal property checking with OneSpin, which has become a formal property checker from Siemens EDA recently, two alternative mutation coverage flows are available. OneSpin includes an onboard feature called Quantify, which does a line-based instrumentation of compiled design model. So it's not the HTL design directly, but the model of it. And it starts by a simple command in the normal property checking environment whenever regular property checking has reached a high completeness level to be checked. Quantify proceeds without any user interaction. Certitude is a tool from Synopsys, which instruments the HTL-Code of RTL designs. As the instrumented design can be read by HTL front ends of any kind of verification tools processing RTL designs, it can be integrated with a wide range of simulators and formal property checkers, even in mixed verification setups, providing common and combinable metrics for all of these. However, the integration is non-trivial and requires deeper knowledge about Certitude and the specific verification tool. Certitude also allows users to choose the configuration of the instrumentation. However, it should be ensured that the common configuration is agreed upon in the organization you work in. The integrated one-spin Certitude qualification flow we present today automates all setup steps and qualification control. All interaction with Certitude is fully encapsulated so that users need no additional specific knowledge beyond what is needed for regular formal property checking in one-spin. Here you see the flow, the regular flow, using Certitude in combination with any verification tool. Certitude has master control, does instrumentation according to user-specified configuration files by running the model phase, which yields instrumented RTL-Code, here indicated by RTL star, with a list of faults to be qualified. Certitude then controls the detection phase by iteratively selecting fault test case pair or property pairs in order to reduce the potentially very high number of detection runs given by the number of test case pairs, test case or fault pairs. It needs to reduce this high number for running the detection run, because each detection run takes at least as long as a normal regression run for each property or test case. In order to reduce, so therefore its numbers, Certitude has a heuristic for the selection of combinations, for example, taking into account nesting of sub-expressions. Each detection run in the verification tool returns a pass or a fail result, which is collected by Certitude in order to update the qualification status and also to decide upon the next pairings. Also, runtimes are used then for this selection. For instrumentation, Certitude allows code reasons, fault categories, and density to be configured. In addition to code-based mutations, stuck-it faults or negation can be instrumented for signals. This example shows a concurrent assignment with several faults injected, one explicitly shown in the lower snippet. For each fault, the effect is displayed on demand in a human-readable way, like in the example where a when condition is replaced with false. The extra window also lists the properties which have detected the faults in a sub-expression, injected in a sub-expression. Just to give you an impression, it is obvious that the generated instrumented code is much less human-readable and orders of magnitude more complex than the original, which also affects the complexity of qualification proofs. Let us now summarize the automated preparation steps of the one-spin Certitude flow. In our flow, one-spin has overall master control. All Certitude setup is done automatically on one-spin side, including background invocation of Certitude for the modeling phase. Then one-spin loads the instrumented RTL star model, formal properties, and triggered by another user command, runs detection proofs without any Certitude control. Certitude is automatically invoked at the end of or intermediately by the user just for generating a report with a final or current qualification status. The user can optionally specify code regions to be instrumented, otherwise meaningful default settings are used. A subset of hold properties can be specified optionally for qualification. By default, all hold properties are used. The execution of all preparation steps is automated. When the instrumented model and properties have been loaded, sanity checks are performed using a global assumption that no fault is enabled. The expectation is that all previously proven properties still hold on the instrumented model. Oh, sorry, what's happened now? Okay. Something happened, sorry. Yeah. So this is the enhanced property, which now contains an assumption about the fault enable vector, which for the sanity check has to be set to 0. So none of the faults is activated, and then we expect that the previously holding property will be proven again. And if this is not the case, this may be due to some subtle effects while the model is non-trivial and the Certitude does some transformation of the original code by instrumenting it. It's not fully guaranteed that each property will hold afterwards. So therefore, we only make sure that only properties which pass the sanity check are used for qualification. After the Sanity checks, the detection rounds are started by another simple user command. As the user may want to prioritize specific subcomponents or properties, the user command for starting the detection rounds accepts code regions as parameters and property subsets. In order to influence the next detection rounds while proofs are ongoing, the user can modify configuration parameters at any time. They become effective after the current round has finished. So the automatic procedure for executing detection rounds repeatedly selects a new property subset most promising to yield detection in a minimum time, adjusts fault assumptions according to the currently addressed set of not yet qualified faults, triggers the detection proofs, and evaluates the proof results, updating all internal bookkeeping kept on one spin side. The iterations terminate either when no more progress is achievable, so either because there are no undetected properties, faults left, or all qualification properties have been proven, which means they cannot detect any further of the remaining faults, or they are just excluded because they hit the configured time limit. So one can decide to increase the time limit and re-include these properties again, the long-running properties, which is a typical scenario. So, and of course, the user can specify a maximum number of iterations he wants to, because if he wants to take some limited control by just trying out some properties first and then other properties, he can do so by just limiting the number of iterations. But by default, it's unlimited. So the automatic termination criteria will then be applied by the procedure. For qualification proofs, the regular properties are enhanced with fault enabling assumptions like we have seen for the sanity checks, but here the enhancement looks different for the qualification for the detection proofs, so that in each detection run, an arbitrary but single fault is allowed to be activated. One hot assumption here, you see. The actual fault selection is done individually and very efficiently for each property by formal proof algorithms, which are highly auto-optimized for the construction of counterexamples, each of which in our context shows an activated fault by which a property failure has been caused. This is the key difference of our formal flow to the normal certitude heuristics. Before each detection round, we only select properties, but not property fault pairs. Thus, by exploiting advanced formal proof technology, we yield much faster progress. If a detection proof returns a hold result, the currently addressed fault subset definitely cannot be detected by that property, which is then removed from the qualification property set for the remaining not yet detected faults of the current fault set. If a property has failed, the corresponding fault having caused the failure is added to the detected fault set and removed from the not yet qualified fault set, of course. So that is not targeted anymore in the next qualification rounds. Mutation coverage collection generally tends to be computationally very expensive due to the large number of runs, and especially in the case of formal property checking, their higher complexity. In this section, we show a few measures for performance optimization. In order to accelerate the detections, we reduce the model complexity and number of proof runs, especially if long runners. Any fault being detected by a fast-running property no longer needs to be addressed by a long-running one, even if the latter one could also detect the same fault. We show later how to adapt model complexity to the number of currently targeted faults. By parallelization, we naturally achieve a great speed up. However, we must take care that the LSF farm or the compute farm is not long overly flooded by too many simultaneous jobs, then the number of which is anyway normally bounded for each user, so that additional job pending times would slow down the overall execution, which would not make sense. One observation gives rise to an optimization regarding provers. The classical approach would be to always generate a counterexample from a reset caused by an activated fault. However, some properties are not provable from reset due to a too large number of preliminary states to be traversed until the property's assumption is met. But they are provable in a superset of the reachable state space by way of provers specifically provided for such scenarios in one spin. Property checking wide or nest counters are example. Given that the examination window of a property handled by a bounded model checker typically just has at most few hundred cycles, it is understood that the 32-bit counter cannot be shown to overflow within a witness trace from a reset. In contrast, with a set of 3 separate properties, one for initialization of the counter, one for incrementation, and one for the overflow case, the counter is exhaustively verified, where the second and the last property are only provable by the prover of group 1, not starting from a reset. We therefore separate properties originally proven from such arbitrary start states from those which require an initial reset state and run detection proofs with corresponding provers only. By this, we get detection results in reasonable runtime for properties which would run for a very long time without result if a prover of group 2 starting from reset were applied. Formal property sets are normally grouped according to function, which is related to subcomponents of the design. A verification engineer can use this knowledge to specify property sets to be run on specific code regions. To the extreme, just a single property can be checked for coverage of a small piece of code not yet qualified. This strategy has the advantage that no wait time for currently irrelevant parts is spent until the user gets the answer to the question whether a newly added property needs further enhancements. Let's take a look at another approach. Using a specific compilation option from OneSpin, model trimming substantially reduces model complexity if only a small subset of the instrumented faults is to be addressed. By tying multiplexer inputs for this fault enabling for irrelevant faults to 0. Doing this once in compilation for a bigger number of qualification runs can be much more efficient than multiply evaluating corresponding assumptions in each single proof. A nice side effect of the repeated model trimming is that when the long-running qualification properties are getting used later on in the complete iterations, because faster ones yield no further contributions, the model has been trimmed according to a smaller number of target faults remaining after the majority of faults has already been detected. Let's add another measure. So a first level of parallelization is already given by jointly submitted detection proofs. In our flow, a second level is introduced by automatically starting by one simple prover user command, several parallel qualification sessions which are assigned distinct fault subsets and operate independently without any overlapping detections. Their results can be merged at any time and added to the global bookkeeping on OneSpin side and then imported into Certitude. In case of automatically initiated parallel qualification sessions, but also if a user has started qualification on different components in individual directories, the same instrumentation is used. The scenario, same design databases. Between the original faults and the faults in the new database are computed, matching the attributes of each pair of faults. Finally, the detection results are mapped to the newly numbered faults of the combined instrumentation. This methodology is particularly useful if in a verification project reused or generated components with less priority are first excluded from qualification and later added if the project schedule allows so. Often a design and corresponding verification still need updates until late phases of the project, either due to inevitable bug fixes or new stakeholder requests. Each design change necessarily affects the fault instrumentation. Restarting the full qualification from scratch every time would be inefficient and to some extent appears needless, since typically only small parts of a design and corresponding properties will be affected. We therefore have added a function for mapping faults from similar but different design versions. However, the results cannot be directly inherited since each change can have side effects even in unchanged portions of the code. Therefore, results are mapped but then rechecked by directed qualification. Since the majority of properties typically still detects the same mapped faults, the qualification status can be restored much faster this way. Only remaining faults with failed directed detections, which can also result from property updates or unmapped new faults, are then addressed by the normal detection procedure. So it's completely safe, this approach, but faster than starting from scratch. For sake of ease of use, just a few basic commands with simple optional parameters are sufficient for running the automatic procedures of the once been Certitude flow. The first two commands, which are here printed in bold characters, are normally sufficient. They can be run without any user-specified parameter, but the user can specify optionally some parameters to focus the detection on more important parts first. So they are highlighted here by the parameters, and the commands are highlighted by bold font. The first command does modeling. The second starts the detection rounds. You can simply just call them without any arguments, and that also works. The procedures work, and the heuristics are pretty good, so that they work also quite efficiently. If the CQD command is given a Certitude database as an argument, the inheritance approach is started. So you see that this command is quite overloaded because you have different kind of parameters which have different effects, but basically the same is done. You do the detection on an instrumented design. Parallel sessions are started by the CQDB command. You can specify a number of n, and this is a non-optional parameter because you have to specify how many parallel qualification sessions you want to have. If new properties have been proven in the meantime on the regular design, they can also be added to the qualification property set using the CQA command. This is the typical situation when you find that some regions of the code have not yet been detected by the current property set, and add new properties to also cover these code regions. The CQDM command is therefore merging results from sub-sessions using the same instrumentation. So it's triggered by the command CQDM, but it's also this merge is also done when you call this last command, this visualization of the Certitude, generation of the Certitude report, because for this also all the results from the subdirectories are automatically loaded into the central bookkeeping on one pin side, and also then loaded into Certitude. Then there's another command, the MCQ command, which allows merging results for the same design with different instrumentations, which, by the way, also allows simulation results, qualification results from simulation to combine with to be merged with formal qualification results. It's quite interesting. So the final command, as already said, is therefore generating a visualization of the current status or the final status. It can be run in parallel to the detection rounds, so it doesn't interrupt the detections, but just collects all the previously achieved results up to that point and visualizes them in Certitude. It's really convenient to do this in this way. Yeah, just let me finish with a short summary now. We have seen a mutation coverage-based flow for formal property checking, which exploits specific strengths and capabilities of formal proof technology in order to accelerate the detection progress and minimize the complexity of checks. By high automation, we achieve ease of use of this mutation coverage flow, and also this flow doesn't require any pre-knowledge inside of the verification engineer. The development of this flow has been driven by much experience from formally verified modules of automotive microcontrollers families. We have seen that there's an easy way of generating a nice report in Certitude at any time using the COD-vis command. And we also are convinced that these metrics are very valuable for measuring the quality of the not only the simulation coverage, but also of formal property coverage. But finally, it must be emphasized that even 100% mutation coverage does not guarantee that the design has been fully verified against the specification, which is impossible until you have a fully formal, unambiguous specification, which is normally in reality is unfortunately not the case yet. On the other hand, 100% mutation coverage provides good confidence that at least each part of the design has been addressed to considerable depth by the verification. With this final remark, I would like to conclude my talk. If there are any further questions, you can ask them now, or you can contact me via email using this email address, which is given there on the slide. So then I would open the Q&A session. So if there are any questions, I would welcome them.
Yeah, just hold on. Mike will have some queries to ask you.
Yeah, thank you very much. I hear an echo, so maybe.
Can you hear me, Holger? Hello, Holger, can you hear me?
Yes, I can still hear you.
Okay. Disha, can you get on mute, please? Yeah, some questions from the audience, please, Holger. The first one, is the flow being used productively for sign-off at the moment?
Yes, it is. It has been already in previous product families, but now it's being used much more widely, also at different Infineon sites. So the answer is clearly yes.
Okay. And does the user of the flow need any specific knowledge on top of what was needed for formal property checking of the verified module?
Now, as I tried to explain on this slide, I think it's on the previous, on this slide, they are just really being you can use very simple user commands, which are fully automatically supported by procedures, which do all the setup of Certitude in the background. So you don't need any Certitude knowledge, and you can start this right away whenever you have reached some status in your normal, if you run your normal formal regression, and then you save the result to the database, and then you can start these commands. So there's nothing else needed on side of the user.
Okay.
Does this answer your question?
Yes, thank you very much, Holger. Well, thank you very much for the talk. No more questions. So thank you very much. Thank you.
Yeah, thank you for your interest.
Thank you.
Bye-bye.